uh, you
Yeah,
are this video is being recorded, right?
exactly. Yeah, yeah. I just now I switched on that recording.
Okay, I think I need to
No, sir. No,
only.
no, no. It's from our side, host side. It is being recording now.
Okay, only thing is probably I might have to keep my entire screen on. Sometimes I had faced some problem
Oh, okay,
with a particular tab. Okay,
okay.
that's okay.
Yeah. Then in that case, yeah, it's better to share the entire screen instead of rather than
Yes,
sharing only the window, the particular
that's
window.
right.
Yeah. So yeah, before starting, let me introduce you to the participants. Good evening, participants. Welcome back to NMR workshop. So it's our fourth day, um, and as like the previous sessions, the coming sessions may be a little advanced topic of NMR. Especially, we are starting today the biomolecular NMR spectroscopy, and it is more a research topic rather than the, especially if you are a chemistry background. So it may be, yeah, little advanced topic to you. So before starting today's technical session, let me introduce our guest, Dr. Mallikarjunaya sir. Um, he is working with the Department of Physics, Ramaya University of Applied Science, Bangalore, and he is an accomplished experimental spectroscopist with an emphasis of magnetic resonance techniques. And he did his MSc in physics with specialization of spectroscopy, and his PhD is from Bangalore University in collaboration with Indian Institute of Science, Bangalore. And then he did his postdoctoral training in biophysical chemistry at University of Arizona, USA. And as a doctoral researcher, he extended his field of study into biological systems with special focus on their biophysical properties. And he has developed broad scientific skills in many key research areas with hands-on experience as an independent researcher and working in a group. And through his continuous endeavor, he aims to contribute towards addressing major concerns in the field of health, food, and engineering science. And apart from the research career, over 20 plus years research and teaching career, he is good in the administration skill too. So he worked as in administrative position in University of Bangalore, IISc Bangalore, and the Arizona University, USA. So with this brief intro, I am welcoming Dr. Mallikarjunaya sir to our workshop. Sir, the platform is yours.
Okay, thank you, Shabil, and I hope I am audible and my slides are visible.
Yes, sir, it is. It is well
Okay.
audible and we can see your screen too.
Okay, good evening to all. I hope, what is the typical background of the participants? Academic background? How many?
Majority of the participants are from chemistry background, but few are from physics, biology. Yeah, it is a mix.
Okay, the most of them are PhD students or master students.
It is 50-50. I think 50 of them are PhD scholars, initial stage of PhD, and 50% are master's students. Yeah, we
Okay,
can say majority are PhD students.
okay, that's great then. And my appeal to all participants, uh, majority in the sense, majorly students. Okay, since this is a workshop, hence feel free. And since I am continuing my session for the next day, that is tomorrow also, okay, I'll try to go slow and introduce sort of, though he already in the sense mentioned it, that I might touch upon advanced topics. Along with that, my general tendency is that I try to give little intro. Okay, and it might be repetitive for some of you. Okay, please bear with that. so that I can take it to the advanced level towards the end, okay, where the simple concepts emerge as a major insightful information. Okay. Now, this topic was given as NMR spectroscopy for biomolecules. However, my current title would be NMR spectroscopy of nanomaterials for biological and material science applications. Today, I would be concentrating on biological for biomolecules, how this NMR spectroscopy would be useful. And in tomorrow's session, I would try to touch upon the material science aspects. Being a physicist, okay, I am concentrating on both parts. In my entire presentation, all of you, I know that you are concentrating on, or if you are a biologist or a chemist, you would be concentrating on solution NMR. However, in my entire talk, I would be concentrating or highlighting towards the solid state NMR. I will try to convince you that why did I choose this solid state NMR, and what are the other side of routine solid state NMR work people have been doing across the world globe. Okay, and here basically my topic. Okay, some modifications I am going to do it here and there. Okay, basically I will be talking about different types of materials. Okay, my entire topic, 1 minute please. Okay, yeah. I hope whenever I change the slide, you are also able to see the change.
Yes,
Can
sir.
you see
Yes,
my
sir.
slide number 2?
Yes, sir. Yeah, now it's second slide. Outline of the talk.
How about now?
Yeah, it changed.
No, third slide?
Yeah, third
EM
slide.
No, I just, because I have some issue with my laptop, that's why I'm cross-checking now. Are you seeing slide number 3?
Yes, yes. EMW Slack.
Okay, okay, good then. Then it is good. Here, the outline of the talk, our entire spectroscopy, all of you know that it is derived out of this electromagnetic spectrum. And especially whenever we get into any of the material science, that could be chemistry point of view, or to some extent, I can say that biology aspect or physics aspect, electromagnetic spectrum is the Bible for us. In that, we will be choosing NMR spectroscopy. We'll understand slowly why it is essential, or which portion of the electromagnetic spectrum we call it as NMR spectroscopy. Under that, we subdivide for my own research work. Okay, I will be touching upon, in the sense, touch solid state NMR, and probably how many of you heard about the zero or internal field NMR? Anybody among the audience? Please feel free. It is a workshop, not a FDP, hardcore FDP, or any conference. It is not, I don't want it to be a one-sided discussion. Any of you have heard about this zero or internal field NMR?
No, sir.
No.
No, sir.
Okay. Yeah, probably that I will try to touch it in the next session. Okay. Now I'll try to give solid state NMR, brief introduction to solid state NMR and zero field NMR. And these spectroscopic techniques are utilized, or what I can say that explored or exploited to study inorganic materials. That is one of the material system our labs would work on. And second one is lipid nanomaterials. And then when we come to this internal field NMR spectroscopy, we talk about ferromagnetic nanomaterials. Okay, and then we extended it to zero field NMR on thin films, and then we touch upon other aspects as well. And as you can see that my journey in this my personal journey extended from Bangalore University, as you can see at the center, and I went along with that Bangalore University. I worked with the Indian Institute of Science during my PhD time, and then moved on to University of Arizona. That is the place where I shifted my paradigm from physics to nano, or physics to bio, where I spent about 5 years at University of Arizona, where I worked on some of the biological systems. Today's talk would mostly cover on those aspects of that. What are the different types of work? I personally did it. I thought of including some other work. Okay, I was unable to do that. With that, what are the other biological systems one can study? I'll concentrate mostly on the work what I personally did it. But I'll try to connect it to other systems what you would have already come across, or in the future you're going to come across. Okay, and right now I am representing Ramaya University, where our PhD students and our BSc and MSc students, as part of their research work, they also try to utilize solid state NMR or NMR spectroscopy as one of their research areas. Now, as we know that all of us are, since most of you are chemists, okay, all of you have seen this electromagnetic spectrum. That electromagnetic spectrum spreads from radio waves to gamma rays, and after radio waves and microwaves, in that particular region, we talk about this NMR spectroscopy. Okay, NMR spectroscopy, which works, or typically it works in the frequency range of 5 to 100 megahertz. Okay, what once upon a time this was designed, they have taken it from the Banwell. Okay, molecular spectroscopy Banwell, but this has already increased by 1 order of magnitude or 1.5 order of magnitude. Now NMR, okay, it extended beyond 1 gigahertz range. Okay, therefore we were able to go little towards the right also to collect some of the extensive information corresponding to different type of materials under study. And all of you know that after this NMR spectroscopy, we come across electron spin resonance. It is almost analogous to nuclear magnetic resonance. And then towards the right, as you know that all of us are aware of different types of motions which are happening in the system or any molecule whenever we consider. For example, rotation. Rotation of a molecule can be studied with infrared spectroscopy, where my external radiation, that electromagnetic radiation, interacts with the given molecule where the rotational motion is undergoing. I can detect it using infrared spectroscopy. And again, this molecular vibrational spectroscopy comes near this infrared region. Okay, and that is microwave spectroscopy. Sometimes we do call about that. And then if I come near the visible region of the electromagnetic spectrum, are you able to see the cursor movement, guys? Can you see the cursor movement? Yes or no?
Yes, sir.
Yes, sir. Yes.
And that is visible reason we almost come near the electronic energy levels. All of you know that electronic energy levels are too far away from each other, and in every electronic energy level I will be having more vibrational energy levels, and within that vibration energy level I will be having several rotational energy levels. Okay, therefore I need less energy to make molecule to rotate. Okay, I need more energy for molecule to vibrate. Okay, different types of vibrations, all of you are familiar with that. And then for electronic state, electronic energy level transitions, I need more energy. This is sort of that I would put it in a way that where the electric field component of the electromagnetic radiation is interacting with the energy levels of these different types of motions. Now, the other one comes under spin reversal. Whenever the spin property of the given molecule, okay, interacts with the electromagnetic radiation's magnetic component, then I come across this NMR, nuclear magnetic resonance, which corresponding to the interaction between nucleus of the given molecule and external magnetic field. Whenever it is interacting, whatever the spectroscopy we study, we call it as NMR. In the similar fashion, when electron spin is interacting with the external magnetic radiation, okay, in that sense, I'll talk about little more in the upcoming slides. Okay, that we call it as electron spin resonance. And just for the completeness sake, if I consider whenever the innermost electrons are knocked off, then we come across X-rays. And within the nucleus, whenever the rearrangement of the nuclear particles happen, that becomes gamma rays. Gamma ray spectroscopy, all of you know, all these different spectroscopic techniques are unique in their own perspectives, and to understand the complete mechanism happening in a given system, probably we need to rely on, that is, one spectroscopist should rely on another spectroscopy technique. Okay, they are all complementary techniques per se. Okay, and now we are restricting our discussions to this spin reversal techniques, NMR and ESR. Now, what is NMR? As you know that it is a technique which exploits the properties of the nucleus. The expansion for NMR is nuclear magnetic resonance. Okay, and what is nucleus? As we know that nucleus consisting of protons and neutrons, and these protons and neutrons do possess magnetic moment. That is, they behave like a tiny magnet. Whenever I keep this tiny magnet in the presence of magnetic field, okay, and then these tiny magnets start precessing around the direction of the static magnetic field, okay, at a particular frequency. Okay, and that particular frequency depends on what type of nucleus I have taken and what is the strength of the nuclear, strength of the external magnetic field we have taken. Okay, and these are the, what I can say, that different techniques. Sorry, I got distracted from this call. Okay, what we are considering here, basically what we are talking here is a Zeeman effect. Zeeman effect is basically an interaction of, or whenever we keep magnetic moment, whenever we keep a material which is having certain magnetic moment, if it interacts with the external magnetic field, okay, then that interaction we call it as Zeeman effect. Here we are in this NMR, we are talking about nuclear Zeeman effect, where the nucleus or nucleons interacting, the magnetic moment arised out of the nucleons interacting with the external magnetic field would give rise to nuclear Zeeman effect. In a similar fashion, if you spin magnetic moment due to electron spin, if that interacts with the external magnetic field, we call it as electron spin resonance. Okay. In the same fashion, different techniques. The ESR is also called as EPR, and there is an NDR technique. There are different Zeeman effect techniques. Now, right now, let us restrict our discussions to nuclear magnetic moment. Okay, and how does this magnetic moment comes into picture? Because protons and neutrons, they do possess magnetic moments. Now, in this case, what we have taken, when there is no field is applied, all these protons or nucleons, okay, they start orienting in different direction, random direction. Then hence there is no net magnetic moment associated with that. The moment I insert my material in the presence of external magnetic field, immediately all these nucleons, some of the nucleons start precessing, in the sense some of the nucleons start, all the nucleons start precessing around the magnetic field, but the graphical representation shows that some of them magnetic moments start aligning in the direction of the magnetic field. Some of the magnetic moments start aligning anti-parallel to the direction of the magnetic field. This is the classical picture. Okay, whenever this happens at this point, if I apply electromagnetic radiation of the same frequency at which they are precessing now in the presence of magnetic field, then I can always reverse the orientation of the spinning axis. Okay, that we call it as that. At that point, our nucleons or nucleus absorbs the energy from the radiation, whatever we have given, and that in the sense later that gives the resonance signal. That resonance signal we call it as nuclear magnetic resonance. All of you, because already 2-3 classes are over, you are already familiar with this basic concept. Just for the completeness sake, I reiterate it. And all of you might be knowing that, can I observe NMR of all the nuclei? Yes or no?
No.
What is the reason? Why I am not able to observe NMR of all the nuclei? Yes, guys, please treat it as a regular class to some extent. Okay, then you will never ever forget at the later stage. Yes, any quick answer? Why we cannot observe NMR of all the nuclei? Sorry?
Sir, because it depends upon the spin, and some of the nuclei also have zero spin. So
Yes. Okay. That because I cannot do NMR for all the nuclei. Okay. Because some of them, as we discussed in the beginning here, these nucleons, they possess like a tiny magnet. When do they possess like a tiny magnet? Whenever like one spin is up, other spin is down, then the net magnetization is zero for that. If you carefully look at that, okay, or look at this particular system, there are 3 arrows are pointing upwards and 2 arrows are pointing downwards. Therefore, 3 atoms are aligned parallel to the magnetic field and 2 are aligned in the opposite direction. If all of them are equal, if I have only 6 atoms, 3 are up or 3 are down, then there is no net magnetization associated with that. Okay, that kind of equivalent system happens in very few atoms. Okay, those atoms we will try to understand it later after the next slide. Okay, now let us understand what is NMR. As the same information have given in the different version, it is a Zeeman effect. Okay, because different nuclei are having different magnetic moment associated with that, and this magnetic moment is zero for certain systems. Okay, the net spin is zero for that system. Then the whatever the orientation, one is parallel to the direction of the magnetic field, other one is anti-parallel to the direction of the magnetic field, can be quantum mechanical picture. And according to quantum mechanical picture, I can show it in these kinds of 2 energy level system. One is parallel system, okay, and another one is anti-parallel system. At that point, this is the same pictorial representation analogous to our previous slide. Okay, when all these spins start precessing around in this direction, basically equivalent to the low energy level system. Now, whenever I shine electromagnetic radiation to the given material, okay, what would happen? Please pay attention here. Our typical magnets. Okay, how many of you have already recorded the NMR spectrum yourself, or you have given sample to them and they have recorded it for you? Yes, guys. Anybody has already recorded the NMR spectrum? Yes. Typically, what we do? Yes. You have recorded. Okay. Typically, our NMR spectrometer looks like that. This is the superconducting magnet where we insert the probe, and there is an inductive coil. Okay. At that point, I insert my sample. Okay. And then what I do now, I have kept the sample in the presence of external magnetic field. Sorry. In the presence of external magnetic field, I have kept the sample. Immediately, two energy levels already got separated. Initially, only one energy level was there. Now, that energy level got split into two energy levels. Now, I need to apply electromagnetic radiation to the system. For that, what I do, since it is a radio frequency signal or whatever the absorption occurs, the energy difference between these two energy levels is equivalent to delta E, and this delta E, if I write it in terms of frequency, that frequency will be in the region of radio frequency, that is 10 to the power of 6 hertz in the megahertz region. Okay, and this any signal generator I can take, our frequency generator. Okay, from that I can set the frequency almost equivalent to radio frequency, and then whenever I shine or whenever I send that radio frequency signal through this coil here, then absorption occurs. Okay, my system would absorb the electromagnetic radiation, and then once they go to higher energy level, they immediately come back to lower. My atoms would go to higher energy level, and immediately they emit the radiation, and that emission of the radiation, okay, can be recorded as a function of time. Okay, that recorded NMR spectrum, we call it as FID. What is FID? If any one of you have already performed this experiment? Yes? Anybody? If you are having it, otherwise I don't bother you again and again. If you know that, please tell me. Otherwise, tell me, I don't know. That is your job, you explain. Then I won't interrupt. Yes, guys? What is FID?
Don't know, sir.
Don't. Okay. Basically, what we are doing is, this is the inductive coil, right? I have passed electricity in the sense our signal in the radio frequency. I have passed it through this coil, and immediately my sample absorbs this energy. And whenever atoms go to higher energy level, and immediately they re-emit the radiation. Okay, whatever the emission of the radiation is picked up by this same RF coil. This is an inductive coil. Okay, it picks up the signal, and the emitted radiation will also be having the same frequency at which you had supplied initially. Hence, this will induce electric current in the circuit, and that circuit amplitude or whatever the voltage induced in the coil is recorded as amplitude of the induced voltage as a function of time whenever we record it. That we call it as free induction decay. Whatever it got absorbed initially, that re-emits. That re-emitted radiation is picked up by this RF coil, radio frequency coil, that will be recorded as free induction decay. Actually, your NMR signal is this one. Okay, this is your actual NMR signal. Okay, all of you got this point? Your NMR, original NMR spectrum looks like this. Okay, I don't know how many of you have recorded, or all of you have, anybody has processed this data, this the problem solving approach in the yesterday's class. What do they do? After getting this NMR spectrum, what do you do typically? Any clues? Yes, guys? Any clues? Once we get this kind of spectrum, I think I am almost sure that none of you have seen this kind of spectrum. You won't believe me. This is my NMR signal. Yes. How many of you believe me? Yes. No one? Okay. Basically, what we do. Yes. Please continue. Yes, guys. Can I proceed?
Yes, sir.
Okay. This free induction decay signal, what we do is we do the Fourier transform of this signal. Then it becomes a frequency domain signal. We convert time domain signal into frequency domain signal mathematically. Okay, that's why it is called in the sense the recent days it is called as FTNMR, Fourier transform nuclear magnetic resonance. Okay, originally data will be collected in the time domain, and before the data is given back to a customer or a student from the operator, he does the Fourier transform and then give it to you. That's why you would not have seen NMR signal in this particular fashion. But this is the first step of NMR recording. Okay, now I hope all of you understood what NMR means. Basically, I keep my sample in the presence of external magnetic field, and the magnetic movements in the given system start precessing around the direction of the magnetic field. I will supply external electromagnetic radiation of right frequency. At that, immediately they flip their angle from this parallel direction to anti-parallel direction, or vice versa, you can consider. And then whenever there is a flipping happens, okay, that data is recorded as an NMR signal. Okay, that gives lot of information as you are already aware of it. Okay, this is the recording or basic fundamental principle of NMR detection. Okay, now as we know that what is nuclear magnetic resonance. Okay, oh sorry, little variation happened. Oh, sorry. Oh, there's a system change. That's why a lot more rearrangement happened. Okay, conventional NMR means that is what a chemist, biologist, or physicist, whoever looks into the material scientist, what is conventional NMR means? Okay, there is a technique. It probes NMR spins and hence quantifies the structure and dynamics of the molecular system. Okay, what is the difference between structure and dynamics? Okay, let us first understand. Okay, what are the different techniques, different types of NMR people use? One is solution state NMR, second one is solid state NMR, third one is MRI. Okay, I hope all of you have heard about MRI, right? What is MRI? Quickly, anybody is aware of that? Magnetic resonance. Yes.
Magnetic resonance imaging.
Magnetic resonance
Resonance imaging. Okay, now let us try to look at that. What are the, where do we use what type of technique? Okay, your solution NMR, the major aim of the solution NMR is to find the structure of a given molecule. In the analogous way, in solid state NMR, along with the structure, one can measure the dynamics associated with the given molecule also. In MRI, why are we using MRI? Where do we use an MRI?
medical search scanning.
What is the purpose of using that MRI? Anybody
Identify the
quickly?
problem, sir. Diagnosing.
See the internal structures of the body.
Huh? Yes, tell me. You're close. Usually, MRI used for whenever fracture happened to the bones. Do we use MRI? Hmm? When do we use an MRI? Or which part of the body most of the people use it? Where? See here, MRI is not a curing technique, or it is not from taking MRI, or it is not a curing technique, it is only a diagnosing technique. From MRI, one can detect where is the problem. Okay, usually MRI is used whenever there is a problem in the soft tissue area of the human body or any other body. Why do we go for soft tissues only with MRI technique? Because our NMR is in the frequency range of radio frequency. All of you know that we use our mobile phones and different signals are being transmitted through air, okay, in the radio frequency. All our FM radios, we are going to hear songs. Okay, that radiation is not affecting our human body very much. Okay, the effect is minimal. But if something has happened to your brain, okay, or something has happened at soft tissue portion, when girls or ladies, whenever they have a baby, okay, at that point, usually they don't prefer for X-ray for any of the diagnosis purposes. They go for MRI because soft tissue should not be, it is easily damaged whenever I use higher energy radiations for any of the diagnosis purposes. Okay, MRI you mostly use for your brain tumor. Most of the material is soft tissue that should not be overheated or that should not be damaged because of the high energy radiation techniques like X-ray, gamma ray. We don't use it because that soft tissue should be taken care for that purpose. Okay, that's why MRI has become, over the years, it has become more and more popular for diagnosis purposes. Nowadays, the newest technology is that people are coming up with handheld MRI machines. I think all of you would have seen so far only MRI. Whenever I want to take MRI, I have to keep all my ornaments outside and no magnetic material should be taken with me. And our entire body is inserted in a cave type of a magnet. But newer techniques are emerging in these days. We don't have to take care of that much care. Okay. Now, let us come back to our first two objects. Whatever the technique, solution state NMR, people use it for structure elucidation, and solid state NMR is used for NMR for dynamics and structure for both of them. And what do you mean by dynamics? Okay, what is the difference between structure and dynamics? Structure is, it is like a still camera. Okay, what are the picture we take, right? Whenever I take a picture, you will get information. Whenever you click the button, what is the posture, in the sense how my hand, at what position I was holding my face, only that picture will be recorded. But in solid state NMR, not only structure, dynamics associated with that also will be recorded. I hope if you are looking at my screen, or if you could see my video also, along with that, you would be observing that whenever I am talking, okay, by default, there will be little motion associated with my head, okay, and little motion associated with lids of my eye, okay, and little motion associated with my hand during the explanation, and a very, very fast motion is associated with my lip motion, okay, or lip movement. Okay, all these are dynamics, are motions occurring in a given material. All those motions can also be recorded, or those motions can also be recorded and studied using solid state NMR. That is the advantage of solid state NMR versus solution state NMR. Of course, solution state NMR is very much essential for structure elucidation. It's a separate technique as it is, But in solid state NMR, along with the structure, the dynamics associated with a given molecule can also be studied extensively. Okay, my specialization is in this dynamics study using NMR spectroscopy. Okay, and as you know that in solution state NMR, the general terminology are to quantify the NMR signal, we use the term chemical shift. And the analogous way, for our solid state NMR technique, we use relaxation rate studies. That in technical word, we call it a spectral density measurement. Whenever we have to measure what type of motions are happening in the given material, I go with solid state NMR. Whenever I want to just study what is the structure, what is the primary structure, secondary structure, tertiary structure of a given molecule, I go with solution NMR. Okay, and if something has happened in your body, okay, and that, for example, if you broke your leg, okay, if bone is broken, immediately I can take the patient to the X-ray, and immediately fracture in the bone can be detected by X-ray. But if there is a small change or some brain malfunctioning is happening, brain tumor is there, I cannot take X-ray. X-ray is high energetic beam, okay, that would destroy most of my content in the brain. That's why I cannot use it. For that purpose, what they do is they go for MRI. At that point, to record the NMR spectrum, they will just add some contrasting agents. Okay, there are all some ferromagnetic material. They try to add up so that they can get better image quality. Okay, and this technique is mostly used by biologists, and solution NMR is mostly used by chemists as well as biologists, and the solid state NMR is used mostly by physicists. Okay, and I hope, do we have MSc physics students? Anybody? Yes, guys, any physics related students?
Sir, PhD scholar, sir.
PhD scholars. Anybody is using NMR as a technique?
Yes, sir.
Oh, that's great.
Sir,
Okay.
is it
Now,
possible to do with NMR for natural dyes, sir? Plant
natural
extract.
dyes, yeah, plant extract, we can get it. Now, once I get into some more details, after that, we will have one-to-one discussion. Okay.
Okay, sir.
After that, you will come to know. I am trying to give overall picture right now, so that it is always good for me to know my audience, so that where to concentrate and where I have to add up little more, pay more attention. That's why I'm asking these questions. Okay. Now, during my PhD period,
Okay, sir.
okay,
Thank you.
I was mostly on the solid state NMR, and then it was the hard spot for material scientists and biophysical chemists. Solid state NMR is the only one. Hence, in my future talk also, I will be concentrating on solid state NMR. I do not talk anything about MRI as well as solution state, because in the first few class sessions and the later sessions, many people are experts in this solution NMR. They would explain you, and hands-on experience they were trying to give you. Okay, they facilitate you to analyze your own spectra, but my job is restricted to solid state NMR. Okay, now, as we discussed earlier, we have in a periodic table many elements we have. Okay, and all those elements do have protons and neutrons. Even then, I cannot do NMR of all nuclei. The simple reason is, the first and foremost thing for NMR to be observed, or NMR signal to be recorded, for that system, the nucleus spin quantum number I should be a non-zero. Okay, then only I can have NMR signal. Okay, only nuclei with spin number, that is spin quantum number I, is not equivalent to 0 can absorb radiation and also emit radiation. The magnetic moment Mi, Okay, magnetic quantum number for the spin quantum number I, the allowed values are -I to +I. As you know that the way our electronic or orbital quantum number, it can go from -L to +L. Here also the spin quantum number can go from -I to +I, giving rise to 2I plus 1 different orientations along the directions of the magnetic field. For example, I is equal to 3/2. We know that 2I plus 1 is given by 4. Okay, 3 plus 1. 4 orientations are possible. One orientation is -3/2, -half, +half, and +3/2. Okay, because it is little difficult to explain this classical picture for all of them, we switch over from classical picture to quantum mechanical picture. All these energy levels, instead of showing an arrow mark precessing around the static magnetic field, I start showing energy levels. One level, one horizontal line, second horizontal line, third horizontal line. Like that, we change it. Now, let us assume that what are the systems for which we cannot record the NMR signal. A nucleus with an even mass number A and even charge, that is atomic number Z, okay, for them the nucleus spin I is 0. Okay, for example, carbon 12, oxygen 16, okay, and sulfur 32, all of them, their spin quantum number is 0. Therefore, I cannot record NMR signal. Okay, but some of you would have already recorded the carbon NMR, right? Anybody has recorded carbon NMR? Yes?
Yes, sir.
Yes, that, okay, whenever we are having even mass number and even charge number, okay, this is for carbon 12, it is, what is that? 6 and 12, okay, 12C6 or 16O8, okay, 32S16, okay, they are having even number for both mass as well as charge or atomic number. For them, we cannot record NMR signal. The second one is whenever a nucleus with even mass number but odd charge number. This is, what is the first one? They have the spin quantum number I as integer. Okay, for example, the first one is deuterium, where 2H1, other one is boron, okay, and the next one is nitrogen. I can record the NMR signal for nitrogen, boron 10, and deuterium. In the similar case, a nucleus with odd mass number, okay, A and odd, whenever we are having odd mass number, they will be having spin quantum number I as half integers, okay, odd integers. For example, hydrogen. Hydrogen is also called as proton in NMR terminology because hydrogen molecule or hydrogen atom is having only one proton. That's why we call it as proton NMR most of the case times. Okay, other one is what you record carbon NMR as a chemist or biologist. Okay, most of the times or whenever you record it, that is due to carbon 12, carbon 13 nucleus, you are going to record the NMR signal. Similarly, 15, nitrogen 15 and phosphorus 31. They can be detected very well. Okay, I hope, is it clear to all of you for what systems I can record the NMR signal during your Viva or during your interview? These are the prominent questions they would ask, whether you know the basics of this NMR. Is it clear to all of you guys?
Yes, sir.
Yes, sir.
Yes, sir. Now I'll talk about that another type of NMR. That is, in a conventional NMR, what I do is I apply magnetic field externally and I can study only NMR active nuclei. And for those nuclei, I can study the NMR spectrum. Usually the prominent nuclei studied are hydrogen, carbon, phosphorus. These are the nuclei what we study. In internal field NMR, zero field NMR, which I am going to talk about it in the next class or tomorrow's class, where to study those kinds of system, I don't need external magnetic field. I can, without applying the external magnetic field, I can record the NMR signal. The example are the materials for which I can record the NMR signal without the application of expensive external magnet or ferromagnetic system, antiferromagnetic system, or ferrimagnetic samples. In those kinds of system, the NMR frequency at which I record the spectrum is, in the sense, exactly decided by the internal structure of the given material. But look at this, our regular conventional NMR spectroscopy. Whatever the sample you take, wherever we have hydrogen, once I insert that sample which is containing hydrogen or carbon or phosphorus, then I can record the NMR signal in 500 megahertz NMR spectrometer or 300 megahertz spectrometer, 400 megahertz spectrometer. Frequency doesn't change. Okay, it purely depends on what is the strength of the external magnetic field I have applied. But in internal field NMR, whenever I want to record the spectrum, I have to change the operating frequency of the spectrometer. That completely dependent on whether I am using iron, whether my compound containing iron, ferrites, cobalt nitrates, okay, and this is some of the systems, manganese containing material, okay, I can do NMR of them without the presence of or in the absence of external magnetic field. That we call it as internal NMR, internal field NMR, or zero field NMR. That let us keep it for the tomorrow's session. Okay, now we'll come back to the biological systems. Okay. Now, all of you know that I don't have to explain this again and again. This is the typical schematic representation, schematic picture of the NMR spectrometer. The central one is our expensive superconducting magnet, in which actually sample can be loaded from the top. Okay, and immediately my sample tube will go and sit here. Here my RF coil is placed here, and that is connected to the console. Okay, where from this console I will give this radio frequency signal to this material, and whenever it absorbs, I record the freely induced signal, and once I do the Fourier transform, I will get the NMR spectrum on the screen. Okay, this is a typical structure of or a typical black diagram of the solution state NMR. Okay, now in the solution state NMR, what really I do in NMR spectrum is a plot of intensity versus chemical shift, and usually chemical shift is measured in parts per million, because the change in frequency from one functional group to the other functional group, the position of the NMR signal is so small. That's why I have to multiply that entire thing by million times. Then only I can see that these peaks are well separated. Okay, this is one of the representative spectra corresponding to that. I think in last few sessions you have studied how to analyze this kind of NMR spectrum explicitly. Okay, and I will not spend much time over there. And basically this spectrum, or whatever the chemical shift is plotted here, is basically a representation of observed chemical shift in downfield from the TMS divided by what is the operating frequency of the NMR spectrometer, either 500 megahertz, 300 megahertz, or 400 megahertz. It will be divided. Okay, the whatever the shift they observe divided by what is the operating frequency of the spectrometer gives the chemical shift. That's why chemical shift is independent of the spectrometer specifications. Okay, I always get, for example, as you can see that there's a trimethyl ammonium group is there, that corresponding peak would appear somewhere around 1. Okay, if I have this methyl group associated with oxygen, then I will get peak only at this particular session. For that, I'll take one reference point, TMS. Anybody can tell me what is TMS? Yes?
Tetramethylsilane.
Yes, tetramethylsilane, where all these tetramethyl, instead of CH3 thrice, I will be having CH3 4 times. All of them are equally spaced. Hence, I will get signal at 0 ppm. Okay, I'm not getting into details, but why this technique is very essential is from this technique, one can get structure of any protein structure. If I want to measure it, I can go up to 100 kilodalton or beyond that in a recent equipments. Okay, I can predict the structure. Our structure elucidation is quite possible with heavy molecules or heavy proteins also. Hence, it is extensively used by many scientists. And you know that because of this extensive usage of these kinds of structure elucidation purposes, okay, NMR has fetched about 6 to 7 Nobel Prizes so far. Okay, that is the strength of this particular technique, how it migrated from physics to chemistry and then to biology in recent decades. Okay, now why I showed it, that is sort of end of my solution state NMR intro. Now, not only this is what most of the people are aware of about the NMR usage, but in reality, NMR is utilized in many fields. Okay, it starts from what we know is the left-hand side structural chemistry, the right-hand side medicine and hospitals and functional imaging. But start from this right below this functional imaging, this NMR can be used in airport for detection of explosives. Okay, that we call it in terms of, instead of nuclear magnetic resonance, slightly we change it. If the spin quantum number is 1 or more than 1, we call it as nuclear quadrupole resonance. Okay, NQR, we talked about it. Okay, then that NQR technique is extensively used in detection of explosives in the airport, and it is also used in many of the industries. Okay, whenever if we want to, for example, food technology, if I want to measure the oil content of a given groundnut or any other nuts, okay, I can quantify the oil content present in the given material. I can use NMR. And in material science, this kind of signal, I'll show it in the next class and explain much better about this. Okay, we'll reserve it for tomorrow. And then all of you know about this particular structural biology system, wherever we are having methyl group, and there will be within the methyl group also we will be having different signals at different locations. The distance between two peaks would give us some through bond interactions, how many hydrogen bonding are present in the given system. All those things can be studied, through which I can detect the structure of a given molecule. Now, this is one of the system, or these two are the pictures where some of the atoms, if they are coming closer to each other, okay, if there is an interaction between these two atoms, what are the forces responsible for these kinds of interactions between two systems or two materials can be detected using NMR. In these two techniques, I will explain it in detail in the later part. This is the biological system what I have taken. Anybody can guess that what is this molecule? What are we representing here? Any biologist?
Lipids, sir.
Yes. Okay, that is the system what I am going to talk from now onwards. Okay, and it can also be used in physics, as tomorrow I will talk more about the physics part of that. And to get the soil science, okay, what is the iron content in a particular soil from one area to other, I can go with what is the magnetic compound or magnetic component of the component is present in a soil. I can use it to quantify the concentration of magnetic component. I can use the soil science and many other techniques we can use it. Okay, now we talked about the NMR spectroscopy. Now we will come back to our solid state NMR spectroscopy. And in solid state NMR spectroscopy, there are different systems one can study. The first one, what we have taken is solid state 2H NMR, that is deuterium NMR. For that, we'll consider lipid membranes, whether there are nano materials, and how one can, in the sense, how one can apply solid state NMR spectroscopic technique to study lipid membranes and membrane proteins is one of the topics what I am going to talk. And at the later stage, probably tomorrow, I will touch upon this application of solid state proton and fluorine NMR to study inorganic metal halides or superionic conductors. And at the later stage, internal field NMR is what our current MSc students and the PhD students are working on. That I will try to touch upon it the next class. Now, let us come back to biology. Okay, what is cellular membranes? All of you know that these membranes are based on lipid bilayers that are impermeable to ions or polar molecules. And why are they using, or what is their function? Their key aspect is to create cellular compartments the way it is shown in these pictures. Okay, these are the cellular membranes, and within these membranes, these proteins mediate distinct cellular functions. Okay, these are the membrane proteins, what we are having it. They perform the particular cellular functions. Okay, the best example for this kind of a picture is take up your skin. Okay, take example of your skin. Your skin is a cellular membrane and your hair is a membrane protein. The way these cellular membranes, can you see that something is emerging out of that? We call it as transmembranes, where it went beyond the dimensions of the membrane. Okay, these are all membrane proteins. Okay, these membranes do, in a sense, proteins mediate particular cellular functions associated with that. Our work, what I am going to talk here, is to study how well these membranes as well as membrane proteins interact with each other to perform certain biological activities is our topic of discussion, or what I am going to talk in next few minutes. Okay, now we know that once from this, as you can see that there are different types of lipid membranes. Okay, they are called with dimeryl phosphocholine. Okay, depending on the length of the chain what we are having. Okay, this portion of the lipid molecule is called as head. This is called tail. Okay, and depending on the length, we give different names. These are all PC corresponding to phosphocholine. Okay, this is dimeryl. This is POPC, DOPC. Again, this PO, DO comes into picture whenever we have unsaturated positions here. Okay, and depending on the what is the composition associated with the head group. Okay, some of them are charged head groups, some of them are uncharged head groups. Will be having it. Whenever we consider any membrane, okay, that will be having combination of all these types of lipid molecules. Along with these lipid molecules, we will be having cholesterols also in the given membrane system. Okay, and all our structure of phospholipids, they vary in with hydrocarbon chain unsaturation, different head group moieties, and cholesterol. These are the different combinations combined together form a membrane. Okay, and this one we call it as you can see it in the next in the leftmost slide. Okay, this number of segments, number of methylene groups, what we have considering here, they are labeled it as C1, C14. This, whenever the chain length is 14, okay, that we call it as dimeryl phosphocholine. This is one of the prominent lipid molecule present in most of the membranes. Okay, any questions here in the biological molecules, what we have considered so far? Yes, guys, any questions so far? Hello? Can I continue?
Yes, sir.
Yes.
Okay.
Yes,
Now,
sir.
what we consider is, whenever we consider, why do we really care about lipid membranes? Because membrane protein functions are modulated by membrane properties due to lipid protein interactions. Most of the things, or most of the people might talk about that, why do you really care about lipid membranes? What we require is proteins. But please remember that these proteins are embedded within the membrane. Okay, whatever is happening to the membrane, okay, that would reflect on the functioning of the membrane proteins also. Hence, it is equally important to study membranes as well as membrane proteins. Then only we understand the complete mechanism associated with the lipid membranes. And our major job in this particular session is that, is there any type of motions which are happening between two lipid molecules whenever we bring them together? All of you know that whenever I talk about lipid membranes, we always talk about lipid bilayers. Okay, there are two layers. One layer where head and head, they come to each other, and tails, they come to each other. This forms one layer, and this forms another layer. Like that, my entire, as you can see in the previous slide, okay, what we have here is bilayer. This is the head group, this is the tail, again tail, head group. Okay, the tails are, they do not like water. Okay, that's why they go away from this water enriched area. Okay, always whenever I talk about this lipid molecules, okay, are membranes, I am always talking about bilayer membrane here. Okay, hence whenever these individual lipid nano materials come together, there are a lot more interactions which are happening over there. There is head-to-head interactions, and then different types of interactions are going to happen. Is there any way through NMR technique I can identify different regimes of intramembrane forces which play important role here? Okay, that is one of the fundamental question one can ask. Second one is, whenever we are having these kinds of lipid membranes, in the presence of external field or external temperature or pressure or any other situation, whether they do deform or not. Deform means, do they change their orientation, their structure? Okay, do they bend or not? That is another question one can ask. If they do bend, then how do I quantify that deformation happening in the given system? Okay, can we get the way a typical physics student would get different? If I bend any iron rod or so, I know that how much is bent, what is the Young's modulus associated with that, okay, bulk modulus associated with that, rigidity modulus associated with that. That kind of different, the quantification of the deformation happening in the system, can we measure it? Okay, is our primary questions what we addressed in our work. Okay, what we are doing it here is, yes, membranes do deform. Okay, and one can measure the way we measure elastic constants for any normal material, for these kinds of bilayer membranes also, for these kinds of particular lipid membranes, membrane materials, lipids also, I can measure those parameters. Okay, that is illustrated in this particular picture. Now, how do these phospholipids ensemble or entangle with each other? We know that I can take a couple of lipid molecules and align them one above the other, and I can perform certain NMR experiments. That we call it as aligned bilayers. Or you just take these individual lipid molecules, okay, disperse in water, okay, then they form multilamellar dispersion, okay, and multilamellar vesicles would be formed, or sometimes for some system, unilamellar vesicles also will be formed. Okay, whenever I study lipid membranes, I can study in these three different versions. Okay, now the same example in NMR, along with the structure, why do we really care about solid state NMR? to answer to that, I need to understand this particular picture. Okay, please carefully look at that. The right hand side, what I am having is, this is the bilayer, this red ones basically corresponding to heads of this lipid molecule. Okay, and this chain is called the acyl chain. Okay, they are like thread-like structures. What we are seeing, they are all tails corresponding to individual lipid molecule, what is shown in the left hand side. Okay, the top one, the extreme top and bottom corresponding to this portion, the head portion of the lipid molecule, and this chain-like structure are called acyl chains. They are entangled here. Now look at this kind of a viscoelastic membrane deformation. Whenever I have a lipid membrane system like that, there are different types of motions associated with that. Okay, one motion is that entire thread, okay, or entire membrane can fluctuate in this particular fashion. Their motion will be in the order of milliseconds. Okay, look at that. In the order of milliseconds, these motions are happening. The second one is individual molecule will be revolving around itself. Okay, can you look at this kind of a picture? This entire molecule is revolving around this direction, or there is a, within this small area, one molecule is moving this side or left side, this side and the other side. This kind of motion occur, they are slow motions, okay, that will be in the order of 10 to the power of -6 to micro to nanoseconds. Okay, motions are happening in the micro to nanosecond regime. The other one is, whenever we consider this individual acyl chain like C7, if you consider, okay, there is a, here C7 means there is 2 more hydrogens are attached to this. Okay, there is a fluctuation variation. A fluctuation is going to happen with these two CH2 groups. The motion associated with the CH2 groups, they are quite fast motions. Okay, and their time scale will be in the order of 10 to the power of -12 seconds. Okay, okay, that is the typical time. Okay, we are going to have it. Therefore, if I want to understand or if I want to quantify the motions occurring in these kinds of system, I need to go with different techniques. Okay, within the NMR itself. Okay, if I measure the NMR spin lattice relaxation time, I can measure the motions occurring in the range of nanoseconds to microseconds. Okay, and this line shape measurement, ESR, EPR, X-ray scattering, all of them one can measure it in this particular time scales. But whenever it goes to this femtosecond, okay, then I have to rely on infrared Raman spectroscopy, at which I can probe the motions occurring in this particular motion, or inelastic neutron scattering and molecular dynamics simulation. But when it comes to this another 10 to the power of millisecond motion, okay, whenever I consider 10 to the power of -3 seconds means that is the time it takes to make one motion. Okay, those can be studied with NMR transverse relaxation time. Please remember, there are 2 relaxation times in NMR. One is NMR spin lattice relaxation time. Other one is NMR spin relaxation, that is also called as transverse relaxation time. These are the measurables from the NMR spectroscopy. What I can measure is from NMR, I can measure NMR spin lattice relaxation time, I can measure NMR line shape, and I can measure NMR spin relaxation time. Whenever I measure all these, whenever I record NMR relaxation, whenever I measure NMR relaxation rate measurements, okay, I can study the motions associated with that. Hence, we rely on NMR to study the molecular dynamics associated with that. However, today I will restrict my entire discussion to how that NMR line shape would be useful to understand the structure of a molecule. Okay, now let us consider here. I think I will be having another 10-15 minutes time, guys. Shibil?
Yes, sir.
Okay. Now, membrane composition, we know that what is membrane composition. Now, let us try to understand what is really happening. Why do I switch over to deuterium NMR spectroscopy in this case? As you can see that whenever I am doing NMR of proton or hydrogen, we know that there are several hydrogens present at every segment C2. Two hydrogens are there. Here, lot more hydrogens are there. Whenever I record the NMR spectrum of hydrogen, I will get NMR signal from all these individual hydrogen atoms present in the given molecule. Hence, my spectrum becomes much more cumbersome, okay, and it will be difficult for me to perform the not to perform the experiment, to interpret the experiment result. Our research groups, wherever I worked so far in last 20 years or 20 plus years, we rely on, in the sense, since you told most of your research students are PhD scholars, there are two ways to get us noticed. Is that either you do simple experiment and its interpretation would be cumbersome, because all simple things will be done by many people. There are many takers for simple systems. Okay, either you do simple experiment and spend years together to explain that whatever the experimental observable and make a paper or publish a paper. The second option is go for very complex experiment where many people cannot do, either due to their experimental restrictions or financial restrictions or their own individual capabilities. Okay. In our labs, what we do is we go for complex experiment. Hence, because there are no, in the sense, we do not have much competition for us. Okay. Our work will be unique in nature. And hence, once we have unique data, okay, it is easy. Our standard models are already available. Our interpretation is very easy. Hence, it is easily publishable. And at the same time, we get healthier information than a conventional spectroscopic technique. For that purpose, what we did in our entire, or whatever the work I am going to show from now onwards, we started replacing all these hydrogens across this acyl chain. We replaced hydrogens with deuterium. Deuterium, please remember, hydrogen, its spin quantum number is half. Hence, it can take only two energy levels, 2i plus 1, 2 into half becomes 1, 1 plus 1, only two energy levels we get it. Instead, whenever we take this deuterium as a nucleus, it has two protons, in a sense, one proton and one neutron. Hence, its spin quantum number I becomes 1. Then number of energy levels become 2i plus 1. That is 2 into 1, 2 plus 1. 3 energy levels. Instead of 2 energy levels, I will get 3 energy levels. And since it is a quadrupolar nucleus, okay, hence, along with the Zeeman splitting, I will be having quadrupolar splitting associated with that. Hence, our NMR energy levels, though in our textbook we always talk that they are uniformly distributed, because of the quadrupolar term comes into picture for the deuterium nucleus. Okay, these energy levels, the 0th energy level slightly shift downwards, and this energy level I is equal to -1 goes up, and I is equal to +1 also goes up. Hence, I get 3 energy levels. Okay, among them, the 2 energy levels, the energy difference increases, and between 0 and 1 state, energy difference decreases. Hence, I will get 2 peaks whenever I observe deuterium NMR. Okay, all of you are familiar with the term, right? For proton NMR, we get only one frequency transition, but for deuterium, we get 2 transitions. Okay, and mathematically, what one can observe in this particular picture, you assume that this is my head group in the right hand side picture, and these are all the CH bonds we are having it. And whenever there is a fluctuation in the CH bond, okay, that can be measured with these notations, whatever you do not have to pay much attention, at least now, to this complex equation. Okay, all this entire equation can be divided or can be written in simplistic with the last word. Okay, what is measurable in our deuterium NMR spectroscopy is our bond order parameter. As you can see that I have written CD. That means this hydrogen has been replaced with deuterium. That's why instead of CH, I have written as CD. Okay, and this deuterium bond order parameter, how well they are oriented with respect to the static direction, okay, can be measured in terms of this mathematical expression. Okay, that would be our experimental measurable in this deuterium spectroscopy. And now this is the fundamental concept of deuterium spectroscopy, which is utilized to study biological systems. Okay, and what are the sub problems we can address here? Now, our fundamental problem is with this NMR, deuterium NMR spectroscopy, one can we measure the membrane deformation? Can we identify different types of forces acting in that? Please remember that I am not a chemist, I am a physicist, okay, and to some extent biologist. To some extent, I try to connect my entire problem statement is concentrating towards this forces, what type of forces happening, what are the material properties one can get, how can I correlate these material properties to some of the fundamental physics problems as well as for the biological applications. Okay, and hence these the questions we addressed over here is to identify the intermembrane forces and to check whether whenever I apply external pressure to the system, whether membrane would deform or not. For that, I utilize this deuterium NMR spectroscopic technique, and we applied different pressure techniques whether to check membranes would deform or not. And then in this study through NMR, we concluded that whenever we apply external pressure, membranes do deform. And once they do deform, okay, one can study that at what point protrusion forces would come into picture, and when do we get undulation forces come into picture. All of them can be measured using this particular NMR technique. That's why it becomes a sort of non-conventional or unconventional way of utilizing NMR for biological molecules. Some of the experimental details would follow now onwards. Okay, the typical lipid nanomaterial, whenever we bring all the lipid nanomaterials together, that form a lipid bilayer membrane, and that can be shown as a single unit cell in this particular fashion. Whenever we are having this kind of a unit cell pictorial representation, there are many parameters associated with that, and all these parameters can be measured using different techniques. And one of the technique is given by Luzarti method. For that, people use XRD, small angle X-ray spectroscopy. From that, one can measure what is the area of cross section of individual lipid. And through solid state NMR spectroscopy, one can measure what is the cross-sectional area associated with individual lipid and what is the length of the hydrocarbon thickness. Okay, what is the interlamellar repeat spacing, that is whatever the big D. From one bilayer to another bilayer will be having different bilayers. That distance I can measure it, and what is the how much is the thickness of the water between one layer to the other layer, I can measure it. And what is the thickness of the hydrocarbon, the head group of the lipid molecule, I can measure it. Okay. And all these things are interlinked with how many water molecules are associated with individual lipid molecule. These are all measurable quantities or derivable quantities out of solid state NMR spectroscopy. All these parameters can be measured using deuterium NMR spectroscopy efficiently and effectively. Now, and the analogous work, detailed 40 page or so, detailed review is published in one of these publications. Those who are interested in this particular technique, you can go through that. And as I told you that the entire work, whatever I am showing it now, it was done at the University of Arizona. Probably tomorrow or towards the end, you will be having one talk from our parent institution, University of Arizona, on NMR experimental technique. Is it right, ma'am? We have one more guest speaker who will be talking about NMR spectroscopy.
Yes, sir.
Instrumentation. Now, look at that. This is the actually recorded NMR spectrum for DMPC lipid molecule. And this entire DMPC lipid molecule, as you can see that C3, C2, C5, C4, these are the different positions across the acyl chain or acyl chain positions across the tile. And once I record this NMR spectrum, this is the typical Fourier transform NMR spectrum. Okay. And once I record the spectrum, I will be able to assign individual peak corresponding to individual portion of the given material. Please remember, though it is a very, 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 very tiny object for which I am recording the NMR spectrum, though it is a macroscopic picture, okay, this deuterium NMR gives microscopic information. Can you see that how beautiful individual peaks corresponding to individual segment along the acyl chain can be recorded efficiently? Okay, let us see the overall picture. How do we come to this final stage? This is the final picture of the signal analysis or data analysis. What we do is, first we record the spectrum, okay, and we try to, this is deuterium NMR spectrum, provides the residual quadrupolar coupling constants, okay, and that residual quadrupolar coupling constants, how do we do that is, first, once we record the spectrum, we fit to multi-Gaussian peaks and we record the area under each peak. And then that entire individual area is recorded. Based on the area, we start assigning how many groups would contribute to this big peak. Okay, how many subgroups? There are 3 groups contribute, like 1 here, 2, 3, 4 subgroups would give me 1 signal here, and this would give me 5th and the 6th group would give me this peak. Like that, one side we get the same signal, right hand side is only a replica of that. As I showed you that instead of observing one NMR signal or one spectral peak, I'll get 2 peaks in deuterium NMR. That's why one peak is towards the lower frequency side, other one is towards the higher frequency side. When I measure the distance between this peak to this peak, that gives me what is the particular residual quadrupolar coupling constant. And once I know this, what is the difference between, this is basically delta nu, right? Frequency difference. Once I know the difference in these 2 frequencies, that can be related to what is the angle at which my carbon deuterium bond got bent with respect to the original notation. Okay. And once I know this delta nu q, I can calculate what is the bond order parameter for this carbon deuterium bond associated with that. Okay, that would help us to calculate the carbon deuterium bond order parameter. And once I know this carbon deuterium bond order parameter, I can calculate what is the cross-sectional area of the lipid molecule and what is the lipid chain length. That is basically cross-sectional area is what is the area occupied this molecule and what is the length of the molecular cell chain. All these things can be measured. I think I am running out of time. I'll start from this point. I'll take another 1 minute or 2 and then I'll close my session for today. Okay, now you have understood from deuterium NMR, I can measure cross-sectional area and acyl chain length. And then you might ask me, so what do we do? Okay, to cross-check that, okay, we wanted to check what is the effect of osmotic pressure membranes, whether they deform or not, we wanted to test. That's why we kept on changing the concentration of water molecule. That is, number of water molecules per lipid, we kept on decreasing. And then we observed that a dramatic change in the signal length shape. Okay, and the distance between these two peaks got increased, and that can be transformed into a measurable quantity called bond order parameter. As you can see that whenever number of weight percentage of water is 3.1, immediately bond order parameter went up. What does it really say? It says that water molecules, whenever they go out, this entire molecule start stretching away from each other. Okay, the real transfer of water from interlaminar space to bulk phase happens. That creates a lot of osmotic pressure in the system that can be interpreted in this particular fashion. From that NMR data, I can measure cross-sectional area, and I know what is the pressure it created in the system. And if I measure the cross-sectional area as a function of pressure, I will get data like this. From this data, the cross-sectional area change with respect to pressure gives us material properties. Okay, from that I can calculate what are the forces included in the given material biological system. When do we have protrusion forces come into picture and ambulation forces come into picture, and I can measure some of the quantities like what is the bulk, what is the Young's modulus associated with that single lipid molecule. One can measure it. And in our case, okay, that the energetics of the area deformation was found out. Okay, we can measure these kinds of biological applications. NMR can be well utilized. Okay, now I would like to stop at this point. Okay, from tomorrow I will talk about this for inorganic and other materials, how same NMR can be utilized. Okay, are there any questions now? Yes, guys.
Sir, I have a question.
Yes, please.
Yeah, sir. So, like, you have explained about the solid NMR stuff, like the deuterated NMR, and like how do we take it for the ferroelectric, ferromagnetic, and all these materials. I mean,
Yes.
you will be explaining in, tomorrow.
Yes.
But my question is, do we use the same software for the analysis?
No, actually, that's what for organizers also had they explained it in the beginning that okay for Savil also here whatever the data I have explained or whatever the technique methodologies I have explained, I do not need any external software. I am not getting number of peaks at different positions so that you can identify whether ketone is present, aldehyde is present, or aromatic ring is present, or what is the J value. All those things we do not do it here. As I told you, in this particular system or tomorrow's system, our measurable quantities are from any software we can measure it. It is only distance between two peaks what we measure. We measure area under the curve at most. We don't need any that NOVA software what we are talking about. Our major intention is on that I'm not using it for
Okay,
my
so sir,
data.
so we will be trained for that stuff also.
Sorry?
Like in the we will be trained when we will be trained with the software in the coming
Yeah.
days. So
This
we will be
is-
trained.
No, during the training, we will not be, especially for me, I am only handling these sessions. Okay. The data analysis is a minor issue. Any software can be used for that. We don't need any dedicated software, or you don't have to do, you don't have to be trained for any of the data analysis. It is a normal data analysis, area under the curve with origin, any Gaussian curves we can do that if it is necessary. Okay, the typical NMR softwares, whatever Bruker or any other software gives, right? Okay, you don't need those softwares to analyze our type of NMR data. Okay, probably you got lost in that position. Okay, we are not, in a sense, at least I am not aware that whether they have scheduled any of the data analysis for my type of research work. Okay, I hope they have not scheduled anything for that. Okay, that's it's not a big deal, what I can say in simple words.
It will be good, sir. Like if, one or two examples of this stuff will also be explained to us while this analysis will be going on. Like hand-on experience on the software, and the analysis of the solid state NMR should also be told. Like one or two examples. It will be really good for us.
Yeah, I'll think about it. Otherwise, you can note down my details. Okay, or you can go through some of our papers. If you have any questions or so, you can contact us. Okay, personal you can contact. Otherwise, let us see that what else can be done in another 2-3 days. Okay, if you have any specific questions, you can always contact me.
Okay, sir. Thank you.
Okay, thank you. And any other question?
Yes, sir. For the curiosity purpose, I'm asking this.
Ah.
Sir, this membrane studies are there. Now, what is the sample which you have taken? Any cell lines or samples? What is the sample you have taken for the studies? Any cell lines?
No, that is DMPC. It's a lipid molecule. Okay, it is readily available in the market. Those kinds of lipid molecules are present in any of our membranes, like our skin or most of the biological systems. Those kinds of molecules are present. That sample, we purchased it. And that's because we wanted this deuterated version, right? Okay, they are quite expensive molecules. Okay, we purchased them.
Sir,
From
if you want to adapt for real life sample, then will this study can be done? Real samples?
No, if you are talking about real time
samples.
No, real in vitro.
In vitro.
Yeah, some people do study about that, because what we have done it is in the deuterium signal. Okay, in the regular or whatever we have it in our system or our biological system, they are not deuterated. Only hydrogens are present. That's why once we understand it at this level, okay, I did not talk about, I only restricted to membranes, not membrane proteins, okay, where one of the GPCR membrane molecule, we extend it and we study it. That I did not discuss in this. Yeah, can you?
Yes, sir, I got it, sir.
Yeah, this is one of the realistic molecule where our group, other members work on, rhodopsin. Okay, in realistic, why we have to study all those things, I did not intentionally, I did not spend much time on that. Okay, this has potential applications in drug industry. Okay, whenever we design new drugs, the first targets are one of these GPCRs. Okay, before we get into membrane proteins, I talked about membranes first. Now, in last 2-3 years, or yesterday, one more paper got published in PNAS where they talk about these kinds of membrane protein effect extensively. Okay, if you are interested, you can visit those papers.
Yes, sir. I got it.
Okay.
Thank you, sir.
Okay. Any other question? Please write to me if you have any questions. You can directly contact me also or through the organizers. Okay. You're free to contact us. Yes.
Thank you, sir.
Thank you.
Some of the topics, like as chemists, we only have knowledge about this solution in NMR. Solid state NMR is very much new to us, sir.
Okay. I hope I was able to give some introduction to solid state NMR.
Yes, sir. Yes, sir.
Was it useful?
Yes, sir. We got an exposure about how the research is going on in biology, cell membranes. This is very much new to us, sir.
Oh, that's good to know. And if you have any doubts or anything,
Yes, sir. We'll contact you.
please write to us any question if you are having it. Okay, I will be more than happy to help you out, or if you need anything,
Thank you. Thank you, sir.
please feel free.
Okay, sir.
Okay,
Yes.
then. Okay, thank you all, guys. Okay, hope to see you tomorrow.
Okay.
Thank you, sir. Thank you so much. See you
Thank you.
tomorrow.
And if you have noted down my number, okay, if you want some topics which should be discussed, if I am comfortable, I'll definitely try to address those issues or those concepts. Okay, regarding, by the time you can always go through my profile, if you have any doubts about my papers where I use NMR, as I already told you that it is sort of a different type of NMR. So Sabil, also I told him that you would not have heard about this kind of NMR. Though solid state NMR in a different way, magic angle spinning, MAS NMR you would have heard of, but not this type of solid state NMR. Okay, if you go through the papers, if you get any doubts, please do ask us. Okay, I'll try to answer to those questions,
Okay.
specific questions also.
Okay, sir.
Okay,
Okay, sir. Thank you, sir.
thank you. Take care.
Yes.